Okay, today we're going to talk about how to construct confidence intervals for a population proportion. Little review of terminology. A point estimate is the value of a statistic that estimates the value of a population parameter. And remember, the statistics are from the sample, the parameters are from the population. And a confidence interval is going to be an interval of numbers that gets generated by a point estimate for the parameter in hopes that it will capture the unknown population parameter within the interval. And the confidence level, which we usually write as a percentage, tells us how confident we are that the confidence interval we constructed captures that population parameter, okay? And by a confidence level, what we mean is that if a large number of samples is obtained, and we do go through the same algorithm, the same procedure, to create a separate point estimate and a confidence interval from each of those samples, then a 95% confidence level indicates that about 95% of all of those confidence intervals will end up containing the population parameter. And the way we make the confidence interval is we create a margin of error on either side of our point estimate. And then we're going to add and subtract that margin of error on each side. Okay, so when we're talking proportions, the point estimate of our population proportion is going to be our sample proportion, p hat. Okay, and the mean of all the possible sample proportions, p hat, the mean of all those, let me fix that, it looks like I have a typo. The mean of all the possible sample proportions is going to be the population proportion, which we indicate by a p without the hat. Sorry about that. Okay, and then what we're going to need to do is estimate the standard deviation of the sampling distribution. So if we actually had all these many large numbers of samples of the same size, and we could calculate their mean, we should get p for the mean. And if we were going to calculate the standard deviation, what we would do is we would do p times 1 minus p, we would divide it by n, and we would take the square root. We don't have a whole bunch of samples, we just have our one sample. So what we're going to use is we're going to use the p hat where there should have been a p, and so we're going to replace this in the formula. And we've seen this formula before, except we've seen it with the population parameter p in there. We don't have that, so we're using the sample proportion instead. Okay? And so actually this should be an approximately equal because it's an estimate. Okay? Okay, and so we're going to do our point estimate, which is going to be our sample proportion. We're going to use that as our starting point, and we're going to add and subtract our margin of error, and our margin of error is going to come from taking a critical value, in this case z, and multiplying it by that estimate of our standard error. So that z, that critical value, is a multiplier. We've used z as a multiplier before. We've used t as a multiplier before when we did means, and we constructed the confidence intervals. So that z value is going to be our critical value. And we're going to get it from our normal distributions table. Okay, so how do we go about this? Okay, so our first thing to do is to verify our assumptions. If you remember when we talked about the central limit theorem for proportions, we said that in order for the sample proportions to be normally distributed, we needed the NP to be at least 10 and the N times the 1 minus P to be at least 10. So we don't have P, we don't have the population value. So what we're going to use is we are going to instead use the P hat in its place. So we need the N times the P hat to be at least 10. And then we also need the n times 1 minus the p hat. So that's basically our complement. That's got to also be at least 10. Okay, so we're going to check that assumption first. We're going to figure out our confidence level. Or else we're going to figure out our alpha if we're given our confidence level. So we basically need our alpha and our confidence level. Then we're going to find our critical value. And we're also going to find our standard error, and it actually doesn't matter what order you do those in. So our standard error, we mentioned it the way that we have. Remember, we're estimating the actual standard error by we're using the formula that should have the population proportion in there, but we don't have it, so we're using the sample proportion instead. Then we multiply that z critical value ends up being our multiplier, so we multiply that times our standard of error. That's our margin of error. And then we're going to add and subtract that from our p hat, our sample proportion, which is our estimate of the actual population proportion. And then that's going to give us our confidence interval. So here are some critical values of z. So you can get all of these from the table, and we've done this before in other lessons. So if you need to write those down or have them all in one place, that's going to be very handy for you to know some of those critical values. Have them very useful in a close place, and you may find yourself remembering them, especially the 95% critical value, which basically comes from taking the 0.005 and splitting it and putting half in each tail. It turns out that that's 1.96. And remember how we said back from the empirical rule that if we had bell-shaped data, about 95% live within, of the data points live within 2 standard deviations of the mean. The 95% is actually associated with 1.96 instead of 2. But it's about 2, right? Okay. So let's work through an example. So let's suppose this is our example. We have a random sample of 537 Americans, and perhaps we did a survey or something, and 173 of them indicated that they frequently ate peanut butter. We want to construct the 90% and the 95% confidence intervals for the proportion of Americans who frequently eat peanut butter. So let's first write down our sample information. So what's my n? My n is 537, right? So then we need to think about creating our sample proportion. Okay, so how many of them, what's my characteristic of interest? Frequently eating peanut butter, right? And it's fairly obvious here, so you could probably get away without writing this down. But sometimes you have to be careful, because you have to be careful with how many of them don't eat versus eat, or if you're talking about some kind of a drug trial, which ones survived, which ones had the side effect, which ones died. Sometimes it's actually not obvious which one to use in your proportion. What you have to do is just pick one direction to use for it, or one characteristic, and then write that down carefully, and then stick to it and be consistent. So in other words, we could do the whole problem in a different way, talk about the proportion of Americans who don't eat peanut butter, and we're going to get essentially the same results. Okay, but our kind of logic getting there will look a little different, but as long as we're consistent, that's the main thing. So my x, these are the number of Americans with the characteristic, that would be 173, right? And so then what is my p hat? My sample proportion. My p hat is x over n, so that is 173 over 537, which is approximately 0.322. You can store this value, but I usually find it easier in this to just round it consistently to 3 decimal places is usually good. Keep in mind that since we're talking proportions, everything's always smaller than 1, so you really have to go out to more decimal places, most likely, than you would need if you were rounding a mean or something else. So I'm just going to use that value. And so then I'm going to go ahead and figure out the complement. So that means that about 0.322 or 32.2% of the people in the sample like peanut butter. And so now we're going to do 1 minus p hat. So I'm going to do 1 minus 0.322. So I'm essentially finding the probability of the complement. So keep in mind every proportion can also be thought of as a probability. And so this gives me 0.678. And I'm going to round them both to 3 decimal places. Okay? Okay, so now let's check our assumptions. So basically what we need is NP times P hat at least 10 and N times 1 minus P hat at least 10. So the way I usually do this, and this is going to help later on when we go to doing hypothesis tests when we compare two proportions, I really like to make a little table. So these are going to be the people who eat the peanut butter, and these are the people who don't eat the peanut butter frequently. Okay, so we have 173 of these, right? So how many are there that do not like the peanut butter? 364. How did we get that? We did the sample size, 537, and we subtract 173. Okay, and so basically what you need to do, and so we could actually make this a little bit of a table, right? Okay, and so this table, so both of these, both this one and this one, both of these are larger than 10. I should say at least 10. Sometimes I'll see larger, sometimes I'll see at least 10. And there's other rules of thumb besides this one that different people use. This, at least 10 is a fairly common rule. And so this tells us that we can indeed use the normal distribution. Okay, so those are two things we need to do at once. So that's the easiest way to think of that NP business. Just basically all of the groups have to be at least 10. So basically all the groups, or all the cells in the table, they must have at least 10. Okay, and so when we go on and do a hypothesis test on two proportions, we're going to also make a little table, and all the cells in the table are going to have at least 10. So it's going to be the same thing, we'll just have a bigger table. Okay, so that's how we check that one. So now what we need to do is we need to find our standard error. So to calculate our standard error, so remember this is going to be the sigma, or the standard deviation of all the samples of that size, all the sample proportions. And so this is going to be P times 1 minus P divided by N. Take the square root, but of course we don't have P, so we are going to use P hat instead. Okay. And so then for us, we are going to use, so what was our P hat? Let me scroll back up. 0.322, and then the 1 minus P hat, the complement, was 0.678. So 0.322 times 0.678. Again, I would just put those in separately, rounded to 3 decimal places instead of trying to get myself doing a whole bunch of parentheses underneath the square root sign. That's just asking for a mistake. And then we divide by our N, which is 537. And there's my square root sign over the whole thing. Okay, so if you do this on your calculator, I would do the whole inside part first. 0.322 times 0.78 divided by 537. Hit enter, and then take the square root of that. Or if you remember the way fractional powers work, you could just raise whatever you get to the 0.5 power, because the 0.5 or 1/2 power is the same as taking the square root. Okay, and so then this turns out to be about 0.020163, and I will store this in my calculator so that I can use it later. So now what we need to do is we need to remember what a confidence interval looks like. They always have this general form, whether we're doing a confidence interval for a mean or for a proportion or for the difference between two means or for the difference between two proportions or for a standard deviation. It's always going to be the point estimate of our parameter plus or minus the critical value of your test statistic times your standard error. They always look like this. So basically what you need to do is you need to remember that you need to find these three things, and then we just fill in the blanks and do it, right? So what do we got? We already know our point estimate. That's our population, or sorry, that's our sample proportion. Critical values, it's going to depend on which confidence level we're doing. Standard error we just found, right? So basically we need to construct each of our confidence intervals. So to do each of them, all we need to do is find the critical value, and then we can plug into this general format. Okay, so the first thing we're going to do is we're going to construct the 90% confidence interval. Let's see, what did it say? 90 and 95% confidence intervals. Okay, so let's start with 90%. Okay, so we need the critical value, right? Okay, so let's do a little sketch. I always make a sketch. Okay, so here's my sketch. So what is my alpha going to be? So my alpha is going to be 1 minus the 0.90, which is going to be 0.10, right? And then what are we going to do with that? Well, confidence intervals, remember, are always two-tailed. So we're going to put half of that into each tail. Okay, so we're going to put alpha over 2 here. So that is going to be 0.1 over 2, which is going to be 0.05. And then over on this side, we also put alpha over 2, which is 0.05, into this tail. Okay, and then the values where the color changes, and these are going to be z's because remember we're following the normal distribution, so this will be z.05, and then this will be negative of z.05. Okay, so we want to go to our table and figure this out. Okay, so notice that the area to the left of z.05 is going to be what? We've got 0.05 in the tail, so it's going to be 0.95. So we're going to look up the area equals 0.95 in our table, and then we're going to pull off the z-score from our table. So let me go to my table. So I want to find the area equals 0.95, and so these all give me small areas that are smaller than 0.5. So I'm going to come down here to the positive versions, and I'm going to try to find 0.5. I'm going to get as close as I can to 0.95. So let's see. Ooh, I think we got it. 0.9495, 0.9505. Looks to me like it's halfway in between those. Okay, so that's 1.6 for the first decimal place there, and the 1's value, and so then we come up here. And so now we've got these, right? So we've got 1.64 and 1.65. What's halfway in between those? 1.645, right? So that tells me that z.05 is going to be halfway in between those, 1.645. And if you go back and look at those common z values I gave you earlier, hopefully we'll find that. And see, we do a 90% confidence level, so area in each tail ends up being 0.05, and we end up with 1.645. So again, remembering those three values or writing them down may be helpful to you, so you don't have to keep going to the table. Okay, and so now we've got the standard error. Let's see, what are we looking for? The standard error, we've got the critical value. We already had the point estimate, and so now we just need to work it out. Okay, so my confidence interval then I'm going to do p hat, that's my point estimate, plus or minus my critical value, that's my z, multiplied by my standard error, and I'm just going to write it down as standard error. Okay. If you want, you can write this down. Plus or minus z 0.05 times the sigma of all the p hats. Okay. And remember, that's what we had to estimate with what we did before. So let's write my upper bound. So I'm going to take my p hat. So what was my p hat? 0.322. That's my sample proportion. Plus or minus my critical value, which is 1.645, times, what was my standard error? Let's look. 0.020163, which I already kept all that in my calculator. Okay, and so for this one, I'm going to use the stored calculator value. So if I stored this in variable A, then I am going to go back and retrieve variable A. And so I'm going to use that. And then I put all this in, and then you will end up having to round it. And we usually round them to the third decimal place if we rounded the proportion to the third decimal place. So I think that 0.355 turns out to be what we have here. Okay, and so, and ooh, hang on, I wrote plus or minus, but the upper bound is actually just the plus. Okay, and so then we're going to do the lower bound, which is the same thing, except this time we're going to put in the minus, right? Okay, and so it turns out when we do this, we should get 0.689. Okay, so it turns out that our 90% confidence interval then is 0.289 to 0.355, and actually it looks like I copied something on there. Sorry, I apologize. That should be a 0.2. Definitely a 0.6 doesn't make sense. This is supposed to be the lower bound, so it has to be smaller than the other one. So I just copied my paper wrong. Okay, so there is our 90% confidence interval. Okay, so now let's look at the 95% confidence interval, and we've done a lot of the work for it already. Okay, so basically, let's look back at what we did before and see what we can still use. We're going to use the same standard error, right, in the same layout. We do need a new critical value, so let's make ourselves a new picture, okay? Because the confidence level is going to matter on that. And actually, sorry, this should be 95%. We already did the 90%, right? 95% confidence interval. Okay, so let's sketch our picture. Okay, and let's figure out what our alpha is going to be. So my alpha is going to be 1 minus that 0.95, so that is going to be 0.05. And so then what are we going to do with that? We always, for confidence intervals, they're always two-tailed, because we've got to add and subtract from the point estimate. So we're always going to put half of the alpha into each tail. And so this is going to be half of 0.05, which is going to be 0.025. Okay, same thing over here. Okay, and then when we label the color change, this is going to be Z.025. This will be the negative of that, or the opposite. Okay, and so now we need to find the critical value. So now we need to look up the area that's to the left of that critical value. So the area left of Z.025 is going to be what? 1 minus 0.025, which is 0.975. So what you would do is you would look up area equals 0.975 in our Z table, and then we'll pull off the Z value just like we did before. And except instead of going to the table again, I'm just going to go back to that little list I made. Okay, so 95% confidence level means 0.025 in each tail, so that puts us at the 1.96, right? This one's easy to remember because it goes along with the empirical rule that we learned earlier. So here's our 1.96, so I mark that on my picture. And then the negative 1.96 over here. Okay, and so now we need to construct our confidence interval. Okay, so we use the same layout as before. Going to do our point estimate, so our p-hat, plus or minus our critical value, Z.025, times our standard error. Okay, so ideally we'd have that. We have our estimate of that we already created. So that's going to give me 0.322 plus or minus 1.96 times that standard error. Let's go look at it again. 0.020163. Okay, so you do your upper bound and your lower bound again, just like you did before. I still have that value stored in my calculator. And so this one is going to give me 0.362 for the upper bound. And then for the lower bound, same thing, except I use the minus sign. And I got 0.282. So our 95% confidence interval is 0.282 to 0.362. Now make sure you remember to always put the small one first. Sounds obvious, but it's easy to forget. Okay, so let's talk a little bit about interpreting these, and let's also look at how these are relative to each other. Let's do a little sketch. So if here's a number line, and here's our point estimate, our sample proportion. So here's our 0.322. Okay, so both of our confidence intervals are going to be centered on that. So let's look at which of these two are closest to it. So we've got a 0.282 for my lower bound, and here we have a 0.289. So the 0.289 is definitely closer. Now my picture here is not going to be to scale. I'm just warning you with that. So I'm going to put my 0.289 here. and my 0.355 here. I just want to get you the idea of where these two confidence intervals sit relative to each other. And I decided, for the sake of simplicity in the picture, not to put an accurate scale on this, but let's think about it. How far is the 0.322 from the boundaries? 55 minus 22 is, what, 37? So about 37 hundredths between those, and same here. Sorry, 33 hundredths between there and 33 hundredths in each side. Okay, so 33 hundredths over. This is going to give me the 90% confidence interval. Okay, so now let's look at the 95% confidence interval. So how far apart is that? 0.82. So that's actually pretty close. That's a lot closer to the 0.289 than it is to the point estimate in the middle. So I'm eyeballing distances here. So those are about it's about 7 hundredths away from this one. So maybe a fourth of the distance. So this would be about, let me just draw an arrow here. This is my 0.282. And then here, this one is, here's my 0.362. And so the distance across these is going to be our 95% confidence interval. So notice which one is bigger. The 95% confidence interval is bigger, and that is definitely always going to be the case. Because basically what happens here is that as you increase confidence, your certainty, then that means you are going to decrease the precision. So if you have to be really more sure, more confident that you've captured the population parameter, then your confidence interval is going to be wider, because if you've got to be more sure, you're going to want to capture some of them that are further out. And so this relationship here always holds. And so where would the 99% confidence interval be? That would be further out still, right? Okay, so let's write down our interpretation of these. So basically what we're saying here is that we are 95% confident that the proportion who frequently eat peanut butter, or whatever your characteristic is, is between 0.282 and 0.362. Hang on, let me check something. What is our 95% confidence interval? 0.362. Oops, another typo. Sorry. This should be a 0.362 right here. Okay, so basically that's what we mean. And it's not really that the probability of the population parameter is in there. The population parameter is what it is. It's just that we don't know. It's more about how likely is it that the characteristics of our sample captured it. And so what that means is if we did a similar algorithm on a whole bunch of samples, in about 95% of those cases, those 95% confidence intervals would successfully capture a population parameter. And of course you can make a similar interpretation for the 90% confidence interval. Okay, so hopefully this helps you get started on constructing confidence intervals for a population proportion. Good luck, and I will see you next time.